When we build a regression model, it's very important to observe that if the model is effective and the model that we have built is a good model or not. Though Box said that all the models are wrong, but some are useful. But still, we use various measures that help us to determine if model is effective or not. One of such measure is the coefficient of determination. When we fit any regression model, there are three sources of variation. One is the total deviation, explained deviation, and unexplained deviation. All these three deviations give us three sources of variation where they can be stated in the form of equation where total deviation equals explained deviation and unexplained deviation. So if we measure these deviations for each value of yi and yi hat and square each deviation and add up to squared deviations, we have sum yi minus y bar square, which is called total sum of square, which is equal to sum yi hat minus y bar square, which is explained sum of square, plus sum yi minus yi hat square, which is unexplained sum of square. These quantities may be considered measures of dispersion or variability. So unexplained sum of square, also known as sum of square of residuals, and it is denoted as SSE. It measures the amount of variability in y that is not explained by the model. To know the amount of variability explained due to regression model, we must know that the total variability present in the data, the total sum of square, which is also abbreviated as SST, is a measure of the total variation in the y variable. Since SSE is the minimum of the sum of square residuals of any linear model, so SSE is always smaller than the total sum of squares. So these explained sum of square can be obtained by taking the difference of the total sum of square and unexplained sum of square. Hence, SSR, which is regression sum of square, also called explained sum of square, can be obtained as SST minus SSE. So using these sum of squares, we obtain the coefficient of determination, which is one of an important measure to find out if the fitted model is good model or not. So the coefficient of determination, which is denoted by R square, is a statistic that explains the amount of variation explained in the dependent variable due to the regression model, even if it's a simple linear regression model or a multiple linear regression model. The interpretation of R square stays the same, which is defined as the ratio of R square, which is SSR divided by SST. And since we know sum of square of regression can be obtained by the sum of square of total subtracted sum of square of error divided by sum of square of total. So using this expression, one can easily calculate R square. Here are some important things to note for R square, that R square ranges between 0 and 1. R square, if it's closer to 1 or it's equal to 1, it indicates that model exactly explains the variability in y. This is the case when in the scatter plot, you will notice that all the dots are falling right on the regression line. And if R square is equal to 0, this indicates that the model does not explain any variability in y, where you will see that there will be a huge scatter in a scatter plot. But that's a rare case. Mostly, R square values are between 0 and 1. If R square value that is larger than 0.5, it's usually considered a significant relationship. A smaller value of R square represents that model is not a good fit, but a larger value of R square represents that this is a good model. But there is a problem with R square, which is called inflation of R square. In any regression model, if we keep adding independent variables to the regression model, R square, though sometimes small, it increases, whether the variable added to the model is important variable or not. So R square can be manipulated by adding variables into the model, it will increase, or by removing variables from the model, it will decrease for sure. Here are some other caveats about it. The independent variables are a cause of the change in the dependent variable. It does not tell us this information. It does not tell us that if omitted variable bias exists. It does not tell us the correct regression was used. It does not tell us the most appropriate set of independent variables have been chosen. It does not tell us if there is any collinearity present in the data on the explanatory variable. It does not tell us the model might be improved by using transformed version of the existing set of independent variable. Or it does not tell us that if there are enough data points to make a solid conclusion. But it simply helps us to discuss that how much amount of variation in the dependent variable is explained by the fitted regression model.